You know, we walk on it, we live in it, we drive over it. Concrete is just everywhere. It's such a fundamental part of our built world, isn't it? We probably take it for granted most of the time. But how much do we really know about this incredible material? You know, the stuff that literally underpins our modern civilization. Today, we're taking a deep dive into the fascinating world of concrete technology. Get ready to have your perceptions, well, cemented.
Indeed. And it's funny you say cemented, because when we talk about something being concrete, we mean it's solid, undeniable, something you can really build upon. And that's exactly what this material represents in engineering. It's the foundation, quite literally.
Yeah.
So our mission today is to sort of peel back the layers of this ubiquitous material, to really understand its core components. It's a pretty remarkable historical journey, and the subtle complexities that make it so powerful. By the end of this deep dive, I'm confident you'll gain a whole new appreciation for, well, the ground beneath your feet and for the structures all around you.
Okay, let's start right at the beginning then. The absolute basics. When someone says concrete, my mind immediately goes to something incredibly solid, unyielding, like a sidewalk or maybe a bridge pillar. How does that everyday understanding connect to the engineering reality? And I mean, where did this stuff even come from?
Yeah, that's a great starting point, because that common usage, that feeling of solidity, it perfectly reflects its primary purpose: strength, durability, solidity. From an engineering perspective, concrete is fundamentally a composite material. That just means it's made of different things mixed together. It's basically a carefully engineered mix of what we call a filler that's usually aggregates like sand and gravel combined with a binder that, well, glues it all together. And that binder is typically cement and water. So unlike natural stone, which you just find in nature, concrete is entirely man-made. It's meticulously designed, proportioned by combining these different elements.
Okay, so it's not just a random mix of rocks and mud like you might think. There's a deliberate, almost like an alchemical process to it. And this concept of a binder and filler, it sounds like it's probably been around for a long time. Where did this innovation actually start?
You're absolutely right. There's a fascinating kind of unseen history behind this man-made rock. The very word concrete itself gives us a clue. It comes from the Latin concretus, which beautifully means to grow together. And that perfectly described how its individual components bind and react chemically to form this unified, incredibly strong mass. It's not just a collection of ingredients sitting next to each other. It's actually a new material formed by their intimate union. Now, believe it or not, the earliest documented use of something like concrete dates back astonishingly far. We're talking about the Assyrians, maybe around 6500 BCE. They were experimenting with early forms of lime-based binders. But, and this is a really critical distinction, their version used what we now call non-hydraulic cement, which basically meant their binder didn't gain strength effectively when it was exposed to water. It hardened mostly by drying out and reacting with CO2 in the air. Ah, okay. So it worked, but only if it stayed dry, pretty much. That significantly limited its applications, right? Made it unsuitable for structures exposed to rain, dampness, or anything underwater. It was a step, definitely, but not the giant leap needed for truly durable, long-lasting structures.
So they essentially had a mix that worked okay above ground, maybe inside, but trying to build a dam or a harbor with that sounds like a huge constraint. Who really cracked the code on making concrete durable in, well, all conditions?
Right. And here's where it gets really interesting. The Romans. They were the true pioneers of durable concrete. They essentially revolutionized construction as we know it. Think about this. They constructed an astonishing 5,300 miles of roads using concrete. 5,300 miles. And then some of those roads are still in existence today, thousands of years later. Some are even still in use, which is just mind-blowing.
Wow, that's incredible longevity.
Yeah, it really is. It's a testament to their engineering genius. Their advancements were huge. They were the first to extensively use both coarse and fine aggregates, the gravel and the sand, in pretty precise proportions. They figured out that a well-graded mix led to denser, stronger, and more workable concrete. And they also discovered this amazing, naturally occurring volcanic ash called pozzolana. When they mixed that with lime and water, it formed a truly hydraulic cement one that could harden and gain strength even underwater. That was a real game changer.
Pozzolana. Right, I've heard of that. And what's also fascinating about the Romans is just how experimental they were. I mean, they must have really pushed the boundaries of what they thought could work, even compared to today's standards sometimes. I remember reading something pretty unusual about their admixtures.
Absolutely. Their ingenuity was remarkable. And get this. The Romans weren't afraid to experiment with some truly unconventional admixtures to, tweak the concrete's properties. Today, Engineers use highly refined chemical admixtures, right? But historical evidence shows the Romans used some really unexpected ingredients. We're talking animal fat, milk, even animal blood.
Animal blood. Seriously, why?
Well, the theory is these might have acted as early sorts of plasticizers, maybe improving workability and flow, or maybe even as rudimentary air and training agents, creating tiny air bubbles to make the concrete more durable against freezing and thawing. They probably just observed these effects by trial and error. And for shrinkage prevention, which is always a challenge with concrete, they even incorporated horsehair into their mixes.
Horsehair? No way! Imagine the reaction if someone tried that today on a modern construction site.
Exactly. It highlights their very practical problem solving and, frankly, their willingness to innovate with whatever materials they had lying around. So this spirit of empirical discovery, this systematic improvement, it really paved the way for modern concrete. After the Roman Empire declined, though, a lot of this knowledge was lost for centuries. It was kind of the dark ages for concrete technology.
Yeah.
It wasn't really until the 18th and 19th centuries that key figures began to rediscover and advance our understanding again. John Smeaton's meticulous research into hydraulic limes in the mid-18th century was crucial. He laid the scientific groundwork. Then came Joseph Aspin, who in 1824 truly brought concrete into the modern industrial era by inventing Portland cement.
Yeah, Portland cement. That's the name we still use today.
It is. He famously named it after the renowned Portland stone, a high-quality building stone from Dorset in England, because the concrete made with his cement had a similar color and appearance. His invention marked a new era of standardized, high-quality, reliable cement. And then, just a few decades later, François Coignet started exploring the fundamental relationship between concrete and steel. His pioneering work laid the groundwork for what we now know as reinforced cement concrete, or RCC. That's the composite material that truly revolutionized modern construction.
Right, the combination, concrete plus steel.
Exactly, combining concrete's immense compressive strength with steel's crucial tensile strength. This pairing is what allowed for the incredible structures we see today, from skyscrapers to vast bridges.
It's incredible to think how much time and, like you said, innovation it took to get from those early non-hydraulic mixes with their very literal animal-based admixtures, blood and horsehair, to the sophisticated, precisely engineered materials we rely on today. It really shows that even the most basic materials have this deep, rich history of trial and error, scientific discovery, and constant improvement. And that acceleration of knowledge in construction, especially from the 19th century onwards, is truly astonishing.
Absolutely, it really took off.
So we've traced concrete's impressive lineage. Now, let's bring it to today. What does this all mean for us? Why is concrete so incredibly popular? I mean, it's adopted everywhere, globally. Yeah. When we look around, it's just, everywhere. Let's unpack its undeniable advantages. What makes it such a star?
Well, you're right. It is a star. Concrete offers a whole suite of compelling benefits that collectively make it the go-to material for countless applications. It's really earned its place. First off, it's remarkably economical. Now, when we say economical, it's always relative, right? We're not saying it's dirt cheap, but it's exceptionally cost-effective compared to alternatives. Think about wood, which you see a lot in colder climates for houses, or steel, used heavily in high-rises and long bridges, or even some of the newer fiber-based composites. And a key reason for this economic edge is its production process. Unlike steel, which needs crazy high temperatures for shaping, or lime, which needs a lot of heating during production, concrete can actually be mixed and cast at room temperature, just ambient temperature.
Ah, that makes a huge difference, I bet. Less energy involved.
Exactly. It significantly simplifies the manufacturing, requires less specialized equipment, and means lower energy consumption during production and placement. That all adds up. Plus, you can often source the main ingredients, the aggregates, locally, which cuts down on transport costs too.
So it's not just the material cost itself, but the whole energy and complexity of getting it into a usable form that makes it economical. That makes a lot of sense.
Precisely. And its next major advantage, and this is maybe one of the most exciting for architects and engineers, is its incredible shape-shifting versatility. Its ability to be castable into virtually any shape. Well, it's an absolute designer's dream and an engineer's workhorse. Imagine a material that starts as a fluid, like thick soup, and then hardens into this rigid, strong form. So whether you need a slender, elegant beam for a modern building facade, or a huge, vast slab for an entire floor, or maybe a massive, intricately shaped column for a complex structure, Concrete can be poured and molded to fit almost any requirement.
Yeah, you really see that in modern architecture, don't you? All the curved buildings, the soaring arches, these really unusual designs. Concrete clearly makes that possible in a way few other materials can.
It really does. It provides immense design freedom. You can achieve complex geometries, flowing curves, efficient use of space, things that might be super challenging or just prohibitively expensive with other materials. That's why you see so many visually striking and structurally innovative buildings made primarily of concrete.
Okay, so it's economical and super flexible in shape. What else?
Well, beyond aesthetics, its practical benefits are numerous and vital for long-term performance. Concrete exhibits excellent resistance to water. This is a major plus compared to materials like steel, which, as you know, is highly susceptible to rust when it gets wet, or wood, which can rot. Concrete structures stand up remarkably well to rain, humidity, even direct water exposure, like in foundations, dams, or marine structures near the sea. This built-in water resilience contributes significantly to their longevity and often reduces the need for extensive waterproofing measures, which saves maintenance costs down the line. And another unsung hero quality, one that provides critical safety, is its high-temperature resistance. Concrete boasts an impressive ability to withstand direct fire for quite a long time, typically up to 3 or 4 hours, depending on the thickness and the specific mix, of course. Even under really extreme heat, the essential CSH gel, that's the calcium silicate hydrate, the main binding glue in hardy cement, it can tolerate temperatures up to about 900 degrees C before it dehydrates and loses significant strength.
900 degrees Celsius. That's impressive.
It is. This inherent fire resistance provides crucial safety in buildings. It gives occupants more time to evacuate and helps contain fires, protecting both lives and property. It essentially acts as a natural fire barrier.
That's a huge safety factor, often unseen but always there, protecting us. And speaking of unseen benefits, I've heard concrete can actually help with waste management. How does that work?
Yes. That's a fantastic point, and one that's often overlooked but becoming increasingly important. Concrete has this remarkable ability to consume waste. This is a significant environmental advantage. It can incorporate various industrial and even some post-consumer waste products as what we call supplementary cementitious materials, or even as aggregates, reducing the demand for virgin raw materials. Think about things like fly ash, which is a byproduct of burning coal in power plants, or ground granulated blast furnace slag that's a waste product from making steel. Even things like recycled glass or finely ground vehicle tires can be used in some mixes.
So you're actually putting waste materials into the concrete?
Exactly. When they're properly processed, these materials can replace a portion of the cement or the aggregates in a concrete mix. This capability not only reduces the amount of stuff going to landfills, which is great, but it also significantly lowers the environmental footprint of construction. How? By decreasing the demand for newly extracted raw materials like limestone and sand, and by repurposing industrial byproducts that would otherwise just be discarded. It's really a win-win for sustainability.
That is genuinely cool, turning waste into a building block.
It is pretty neat. But perhaps concrete's most revolutionary advantage, especially for modern structural engineering, is its ability to work synergistically with reinforcing steel. This partnership forms what we call reinforced cement concrete, or RCC. It's the foundation of almost all modern structures. So imagine concrete as a material that loves being pushed together. It's incredibly strong in compression, right? But it's very weak when you try to pull it apart, in tension. Steel, on the other hand, is excellent at resisting pulling forces. It has very high tensile strength.
Okay, so they're opposites in a way.
Kind of, yeah. In RCC, we embed the steel bars, the rebar, within the concrete exactly where we expect those pulling forces, those tensile stresses, to occur like at the bottom of a beam that's bending. The steel provides the necessary tensile strength that concrete inherently lacks. But the concrete, in turn, performs two vital functions for the steel. First, it protects the steel from corrosion by providing an alkaline environment and acting as a physical barrier against moisture and air. And second, it protects the steel from fire, acting as insulation.
Ah, so they protect each other too.
It's truly a perfect material marriage. Each material compensates for the other's weakness, creating a composite that's far stronger, more durable, and much more versatile than either material could ever be alone. This partnership is what allows for the construction of everything from multi-story buildings to massive long-span bridges. Without RCC, our cities would look very different.
That makes so much sense. It's like concrete provides the muscle, the compressive brawn, and steel provides the stretch and flexibility, the tensile strength. And together, they're unbeatable. And once you've got them combined in a structure, what about upkeep? Is concrete a high-maintenance material over its life?
Actually, quite the opposite. Once a concrete structure is built correctly, it typically requires minimal maintenance. Its inherent durability means it can withstand a wide range of environmental exposures. Think harsh weather, freeze-thaw cycles, even chemical attack in certain industrial settings, without needing constant protection, like painting or plastering, which many other materials require. Unlike materials that might degrade quickly if they're not regularly maintained, concrete structures often stand resilient for decades, even centuries, with relatively little intervention. This makes them a very cost-effective long-term solution for infrastructure and buildings, reducing those lifetime costs significantly.
Okay, that's an incredibly impressive list of benefits. Concrete really does sound like a marvel, versatile, strong, durable, economical, low maintenance. But nothing is perfect, right? Every material has its specific characteristics, its challenges. So what are some of the inherent limitations or, trade-offs we need to be aware of when we're designing with and working with concrete?
You're absolutely right. While concrete is fantastic and incredibly widely used, it definitely has its Achilles heel, or maybe several Achilles heels. And understanding these limitations is absolutely crucial for proper design and construction. Engineers spend a huge amount of time designing around these very issues to ensure safety and longevity. First off, concrete is described as a quasi-brittle material.
Quasi-brittle. Okay, what does that mean in simple terms?
Well, imagine a piece of glass. It takes a certain amount of force to break it, right? But once it starts to fail, it shatters suddenly, often without much warning. That's brittleness. Now, unlike ductile materials like steel, which will bend and stretch and deform quite a lot, showing very visible signs of distress before it actually breaks, a phenomenon engineers call strain softening. Concrete offers minimal strain softening before it fractures. It tends to fail rather subtly, with little visible warning.
Oh, okay. So it's strong, but it doesn't give you much notice if it's about to fail under unexpected stress. That sounds like a critical point for safety.
Exactly. It means engineers have to design with careful safety factors built in, especially in areas where you might get unforeseen overloads, to prevent abrupt and potentially catastrophic collapses. And this leads us directly to its most significant inherent drawback. Concrete possesses very low tensile strength. While it excels under compressive loads, meaning it's incredibly strong when being pushed or squeezed, which is why it's great for columns and foundations, it's quite poor at resisting pulling or stretching forces. Think of trying to stretch a concrete block versus just pushing down on it.
Right, you can push on it all day, but pulling it apart seems impossible, or rather, it would just snap.
Precisely. To give you a sense of the disparity, its toughness and tension is roughly only 150th to maybe 1100th that of steel, a huge difference. And this is exactly why it's almost always paired with steel in reinforced cement concrete, or RCC. The steel provides that necessary tensile strength to resist the pulling forces that concrete just can't handle on its own. It makes up for concrete's inherent weakness. Without that steel, concrete structures would crack very easily under even modest bending or stretching.
Okay, so low tensile strength is the big one. What else?
Another limitation relates to its weight, or density. Concrete has low specific strength compared to materials like steel. Specific strength just refers to a material strength relative to its density or weight. So this implies that for the same weight, a steel element will generally be much stronger and can carry significantly more load than a concrete element of the same weight. This often means that concrete structures need to be much bulkier, have larger cross-sections, to achieve the same load-carrying capacity as steel structures.
So if you want something super strong but also relatively light, concrete might not be your first choice unless you make it much, much bigger.
Exactly. While concrete often wins out on overall bulk cost, this need for larger sections can lead to heavier structures overall. And heavier structures, in turn, mean you need more robust, potentially more expensive foundations to support them. So it's a trade-off. This is why for very tall buildings or very long-span bridges, you might see a preference for steel in certain key elements because of its higher strength-to-weight ratio.
Got it. Heavier, bulkier for the same strength. Makes sense. What about actually building with it? Any limitations there?
Yes, definitely. From a construction perspective, concrete doesn't magically hold its shape when it's wet, right? It's like a thick liquid. So it requires form work. These are temporary molds or structures, often made of plywood, steel, or sometimes even plastic, that you pour the wet concrete into. These forms support the wet concrete, giving it its final shape until it hardens enough to support itself. Designing, fabricating, erecting, and then later dismantling this formwork is a really significant part of any concrete project.
And I imagine that adds quite a bit to the construction process.
Oh, absolutely. It adds significantly to both the construction time and the overall cost. Plus, the proper design and careful erection of formwork are absolutely critical for the final shape, the dimensions, and ultimately the structural integrity of the hardened concrete element. Any error in the formwork, if it bulges or leaks or isn't aligned properly, can lead to costly rework or even serious structural deficiencies down the road. Furthermore, once you've poured the concrete into the formwork, it needs a long curing time for proper strength development. It doesn't just harden instantly. The chemical reactions that harden cement, which we call hydration, are exothermic, meaning they actually generate heat. Now, if this heat isn't managed properly, and crucially, if the concrete isn't kept moist, especially in the early stages, rapid water evaporation can occur. And this rapid drying leads to significant shrinkage and, inevitably, cracking, which compromises its durability.
So you have to keep it wet, like watering a plant.
Kind of, yeah. Proper curing is essential. This usually involves keeping the concrete surface continuously moist for a period, typically for at least 7 days, and often up to 28 days for full-strength development, depending on the conditions and the type of structure. This might mean using sprinklers, covering it with wet burlap sacks, or applying special chemical curing compounds that seal the surface. This lengthy curing period is absolutely essential to ensure the concrete reaches its intended strength and durability, and to prevent internal stresses and potential future problems. But it does mean construction can't always proceed at breakneck speed immediately after pouring. There's a waiting game involved.
So it's not just about pouring it and leaving it. It's this careful process of almost babying it while it gains its strength. And that leads neatly to the final limitation you mentioned, doesn't it? Cracks. Why is concrete so prone to cracking, even with all these precautions?
You've hit on a persistent challenge. Despite best practices, careful design, proper curing, concrete is inherently prone to developing cracks. It's almost unavoidable to some extent. These cracks can pop up due to various factors. There's drying shrinkage, as that excess mix water eventually evaporates over time. There's thermal expansion and contraction from daily and seasonal temperature swings. Concrete expands when hot, contracts when cold. And of course, there are cracks from the applied loads the structure carries. Now, while some cracks are minor and just superficial, we often call them hairline cracks, and they might not be structurally significant. Others can be wider or deeper and potentially compromise the structural integrity or the long-term durability of the element.
How do they compromise durability?
Well, critically, cracks act like tiny highways, allowing harmful substances to get inside the concrete. Things like moisture, chlorides from de-icing salts used on roads in winter or from seawater in coastal areas, or other aggressive chemicals. If these substances penetrate deep enough to reach the embedded steel reinforcement, they can cause the steel to corrode, to rust. And rusting steel expands, which puts internal pressure on the surrounding concrete, causing more cracking, spalling where chunks of concrete break off, and eventually, potentially leading to serious structural failure over time. So managing, mitigating, and monitoring cracking is a continuous challenge and a major area of research in concrete design and construction. Engineers use various techniques like control joints to encourage cracking in predictable locations, proper reinforcement detailing, and specialized admixtures to try and minimize and control cracking as much as possible.
Okay, so quasi-brittle, weak in tension, relatively heavy, needs formwork, needs long curing, and prone to cracking. That definitely balances out the advantages. It's clearly not a perfect material, but one we've learned to work with very effectively.
Precisely. We understand its limitations and design accordingly.
So what does this all mean for us? Given all these pros and cons, is all concrete basically the same stuff, or are there different types we should be aware of? It sounds like there must be more to it than just that standard wet gray stuff you pour on the ground.
Not at all. You're absolutely right. Concrete is incredibly versatile, and we actually classify it in various ways depending on its specific properties and what we want it to do. Understanding these classifications helps us appreciate its adaptability and how engineers can really tailor it for specific jobs, almost like a chef selecting different ingredients for different dishes. One primary way we classify concrete is by its weight per unit volume, or its density. This is really important, especially considering that low specific strength limitation we talked about. At the very light ends, we have ultra-lightweight concrete. This stuff has a density less than 1,200 kilograms per cubic meter. You'd use this where weight is absolutely critical, maybe to reduce loads on existing structures, or for special insulation panels. It can even float on water in some cases. A bit denser, but still lighter than the norm, is lightweight concrete. This falls between 1,200 and 1,800 kilograms per cubic meter. It offers benefits like better thermal insulation and reduced dead loads, making it useful for things like building facades, precast wall panels, or even some non-structural fills. Then we have normal concrete. This is your everyday garden variety workhorse concrete. It's the most commonly used type for general construction, and it has a standard density of around 2,400 kilograms per cubic meter. That number, 2,400 kilograms per cubic meter, is a key figure engineers often have memorized, as it's used in so many basic design calculations for typical buildings and infrastructure. And finally, at the other end of the scale, you have heavyweight concrete. This stuff exceeds 3,200 kilograms per cubic meter. It's made using very dense aggregates like baberite or magnetite ore. Its main use is for specialized purposes like radiation shielding, think nuclear power plants or hospital x-ray rooms, or sometimes for counterweights where you need a lot of mass in a small space.
Wow, so density dictates quite a lot about where and how you'd use it. From floating concrete to radiation shielding, that's quite a range. What about its strength? That seems even more fundamental. Do we have different categories for that too?
Absolutely. Strength is arguably the most critical classification for structural purposes, and we measure it as its compressive strength, typically determined after 28 days of curing under standard lab conditions. It's important to remember, concrete keeps gaining strength slowly over time, for months or even years, due to those ongoing chemical reactions in the cement paste. But the 28-day strength is the standard benchmark we use for design and quality control. We measure the strength in NEM, that's newtons per square millimeter, a unit of pressure or stress. So first, you have ordinary concrete. This typically falls in the range of 10 to 20 nanometers strength. It's suitable for general-purpose use where really high strength isn't the main concern, maybe foundations for small, non-load-bearing structures, or things like pathways or site concrete. Then comes standard concrete. This is the most common category for structural applications, with strengths typically ranging from 25 millimeter up to about 60 millimeter. This is what you'd find in the beams, columns, and slabs of most medium to high-rise buildings, bridges, and general infrastructure projects. It really forms the backbone of our built environment. And finally, anything significantly above 60 millimeter is generally considered high-strength concrete. This is reserved for more demanding structural elements. Think of the slender, heavily loaded columns in very tall skyscrapers, or elements in long-span bridges, or specialized applications where you need high strength-to-weight ratio, or where space is really tight. Engineers are constantly pushing these boundaries, developing ultra-high-performance concretes now that can exceed 150 millimeter.
60 N per square millimeter. That sounds like a lot of pressure.
It is. Imagine roughly 600 kilograms of force pressing down on an area the size of your fingernail.
Wow. Okay. And beyond these core types based on weight and strength, you mentioned specialized concretes.
Right. Beyond these core classifications, we can create all sorts of specialized concretes by adding specific materials, often called admixtures, to enhance particular properties. We won't dive super deep into all of them now, but some fascinating examples include fiber-reinforced concrete. This involves mixing in various types of short fibers, maybe steel, synthetic polymers, or even glass fibers throughout the concrete. The main goal here is to significantly improve its tensile strength and ductility, making it much tougher and more resistant to cracking, impact, and fatigue. You might see this used in things like industrial floors that take a beating, or maybe in blast-resistant structures. Then there's polymer concrete. This uses polymers, essentially plastics, either as binders instead of cement or as modifiers added to traditional cement concrete. These polymers can dramatically enhance properties like strength, flexibility, and especially chemical resistance. So it's great for aggressive environments where normal concrete might degrade quickly, like in chemical plants or maybe sewer pipes. And another interesting one is DSP concrete. DSP stands for Densified Systems with Pozzolanic Microsilica. This type uses silica fume, which is an ultrafine byproduct from producing silicon metal and alloys. Adding this microsilica makes the concrete incredibly dense and strong, leading to ultra-high strengths and exceptional durability. It's used in really demanding applications, like the cores of high-rise buildings or specialized precast bridge elements where top performance is absolutely non-negotiable.
It's really fascinating how one base material, cement, water, aggregate, can be modified into so many distinct variations, each tailored for such specific needs. It really makes you think about how much precision engineering goes into selecting the exact right type of concrete for every single part of a structure, from a simple sidewalk right up to a massive skyscraper.
Absolutely. It's all about choosing the right tool for the job.
Okay, so now that we've explored what concrete is, its history, its pros and cons, and its various forms, let's zoom in even closer. Let's get right down to the fundamental building blocks themselves. What exactly goes into that familiar gray mixture that forms so much of our world? What are the ingredients?
Right, this is where the real magic happens, chemically speaking, where these seemingly simple components combine through complex reactions to create such a powerful and versatile material. The primary ingredients, as we touched on, are cement, water, and aggregates, both coarse and fine. Each one plays a critical and distinct role, and importantly, the quality of each component is paramount for the final properties of the concrete. It's exactly like baking, isn't it? If your flour is bad, or your water is off, or your yeast is dead, the whole loaf suffers. Same principle here. Let's start with cement, the binding force. In many parts of the world, including India, for instance, we commonly encounter different grades of cement. These are often designated by numbers like 33, 43, and 53. Now, these numbers aren't just arbitrary labels. They directly indicate the cement's characteristic compressive strength, again in newtons per square millimeter, measured after 28 days of curing under standard lab tests. So a 53-grade cement, for example, is manufactured to achieve a minimum compressive strength of 53 nanometers at 28 days. Choosing the right grade is absolutely crucial for engineers to ensure the structure can safely handle its intended loads.
So the grade tells you how strong the glue will be, essentially.
That's a good way to think about it, yes. And to ensure consistent quality and safety across the board, we rely heavily on codified standards. For example, the Indian standard, IS codes like IS 269, which covers ordinary Portland cement. These codes aren't just dry legal documents, they're vital engineering tools. They provide precise specifications and guidelines for everything: the chemical composition of the cement, its required physical properties like fineness and setting time, and the exact testing procedures it must pass. They prevent people from just mixing things arbitrarily and ensure a baseline level of structural reliability, which is absolutely vital for public safety. Think of them as the comprehensive recipe and quality control manual for cement. And for students or anyone wanting to learn more, these codes are often available for self-study from bodies like the Bureau of Indian Standards (BIS) website, usually watermarked to prevent commercial misuse. It's interesting, too, these codes get updated with amendments, sometimes telling engineers to disregard older clauses. You can actually see how scientific knowledge evolves into practical standards over time. Now, an interesting and increasingly common component often used with cement are pozzolanic materials. We mentioned pozzolana from the Romans earlier. Modern examples include fly ash or metakaolin. By themselves, these materials usually have little or no cementing property. They aren't binders on their own. However, when you mix them with Portland cement and water, they undergo a chemical reaction. They react with the calcium hydroxide, which is a byproduct of the initial cement hydration. This secondary reaction forms additional cementitious compounds, essentially creating more glue within the concrete matrix. This significantly enhances the concrete's long-term strength, often makes it denser and less permeable, improving durability, and can reduce the heat generated during hydration, which is good for large concrete pours. And as we discussed earlier, using these pozzolans, many of which are industrial byproducts, beneficially consumes waste, making construction more sustainable.
Okay, so cement is the precise graded binder, the main glue. And these pozzolanic materials are like enhancers or boosters that also happen to help the environment. Very clever. But you mentioned water is critical too. I have to admit, I always thought water was just, well, water. How complicated can the water part be?
That's a very common misconception.
Yeah.
And it really highlights just how much precision goes into making good concrete. Let's talk about water, more than just a mixer. The quality of water used in concrete is often underestimated, but it's absolutely critical. It's not just about adding liquid to make a paste you can pour. Water is the key ingredient that initiates the vital chemical reactions of cement hydration. Those reactions are what cause the concrete to set, harden, and gain strength. It's the catalyst.
So no water, no reaction, no concrete.
Exactly. But the quality of that water matters immensely. As a general guideline, the pH of the water should ideally not be less than 6. Generally, water with a pH between 6 and 8 is considered suitable. Water that's too acidic or too alkaline can significantly interfere with the complex hydration chemistry, potentially messing up setting times or reducing the final strength. And here's where it gets really surprising for many people. Excessive impurities in the mixing water can severely impact concrete's properties in numerous ways, sometimes catastrophically. Impurities can affect its setting time, making it harden too quickly, which is a nightmare for placing and finishing, or too slowly, delaying construction. They can hinder strength gain, meaning the concrete might never reach its designed load-bearing capacity. Scary thought. They can reduce its long-term durability, leading to premature degradation and a shorter service life for the structure. You might see ugly efflorescence, those powdery white salt deposits that migrate to the surface. Impurities can cause discoloration, which is mainly an aesthetic issue, but still undesirable. And most critically, certain impurities, especially chlorides, can induce rapid corrosion of the steel reinforcement in RCC. This is probably the biggest concern regarding water quality in reinforced concrete, as steel corrosion can lead to structural failure over time.
Wow, okay, so bad water can really wreck a concrete mix. What sort of impurities are we talking about? Are there specific limits?
Yes, absolutely. Engineers have established specific impurity limits that are generally followed, often dictated by national standards or project specifications. Here are some key ones to watch out for. Organic content. This refers to decaying plant or animal matter like humus or algae. The limit is usually very strict, often around 200 milligrams per liter, MgL. Why? Because organic matter can directly interfere with cement hydration, significantly slowing down setting and reducing strength. Inorganic impurities. These are general dissolved salts and inert particles. There's a broader limit here, maybe around 3,000 milligel. Too much can just dilute the mix and affect workability. Sulfates. These have a tight limit, often around 400 milligel. Higher levels are extremely problematic. Sulfates can react chemically with compounds in the hardened cement paste, primarily calcium hydroxide and calcium aluminate hydrates, to form expansive products like ettringite. This reaction causes the concrete to swell internally, leading to cracking, spalling, and eventually disintegration. It's known as sulfate attack, a serious durability issue. Chlorides. This is the big one, especially for RCC. For plain concrete without steel, PCC, you might tolerate higher levels, maybe up to 2,000 milligel. But for RCC, where steel rebar is present, the limit drops drastically, often to just 500 milligel, and sometimes even lower for really critical structures like prestressed concrete.
Why such a huge difference for reinforced concrete?
Because chlorides are the arch nemesis of steel reinforcement. They break down the protective passive layer that normally forms on steel in concrete's alkaline environment, allowing corrosion or rusting to start much more easily, even if oxygen and moisture levels are relatively low. This is why using concrete near salty environments like coastlines or roads treated with de-icing salts in winter requires special care and often lower chloride limits or protective measures. Suspended material, tiny particles just floating in the water like silt or clay. These shouldn't exceed about 2,000 milligel, as they can coat the aggregates and weaken the bond between the cement paste and the aggregates, reducing overall strength. Water containing more than about 1,000 milligel of certain dissolved inorganic salts, like those of zinc, copper, or manganese, can also directly reduce the concrete's overall strength. Now, for some really surprising effects from impurities, certain naturally occurring impurities such as sodium phosphate, sodium borate, and sodium iodide act as retarders. They slow down the setting process significantly, which can be a problem if you need the concrete to harden quickly for construction schedules or in cold weather. They can also reduce the final strength. Conversely, things like calcium carbonate and carbonates of sodium can act as accelerators, speeding up the setting and hardening. This might be beneficial in cold weather to get things moving, but can be problematic in hot conditions where you want more time to place the concrete before it gets too stiff. And here's a truly fascinating one. Sugar. If sugar is present in the mixing water as an impurity.
Sugar, like from a spilled drink.
Could be. Or maybe from industrial contamination. The effects are highly dependent on the amount. Up to about 0.05% by weight of cement, it has very little impact. However, if it's present at around 0.15% by weight, it acts as a strong retarder, significantly delaying the setting time and reducing the early strength gain. But, and this is the really intriguing part, it actually increases the 28-day strength.
Wow, that's counterintuitive. Slower start, stronger finish.
Exactly. It highlights the complex, sometimes weird chemistry involved in concrete. A seemingly simple impurity can have multiple, sometimes contradictory effects depending on its concentration. Regarding oils, mineral oil, like petroleum-based oils, seems to have a relatively minor effect on strength development if present in small amounts. But vegetable oils, even in small quantities, can be quite detrimental to concrete's long-term strength, likely by interfering with hydration and bond formation. So given all these strict limits on impurities, especially chlorides and sulfates, it becomes clear why using seawater for mixing concrete is generally a big no-no.
Right, because it's full of salt, which contains chlorides.
Exactly. Seawater contains high levels of chlorides and other salts. Using it can lead to several problems. Accelerated setting, making it hard to place properly, ugly efflorescence on the surface, and most critically, severe and rapid corrosion of the steel reinforcement, which could eventually lead to structural failure. Seawater is really only considered as an absolute last resort, maybe in extremely remote coastal or island construction where absolutely no freshwater source is available. And even then, it requires very strict conditions, specialized concrete mix designs, like using sulfate-resistant cement or corrosion inhibitors, and often results in a structure with lower expected durability and higher lifetime costs. It's generally avoided if at all possible.
Wow. Who knew water could be so incredibly complicated and critical in concrete? That's really eye-opening. Especially the part about sugar having opposite effects and the really strict chloride limits for reinforced concrete. It definitely makes you appreciate why water testing at a construction site isn't just some formality, but a fundamental safety and quality measure.
Absolutely. Clean water is essential. And finally, let's talk about the third major ingredient, aggregates, the bulk and the backbone. Aggregates, which include both coarse aggregate, what most people call gravel or sometimes grit, and fine aggregate, basically sand, make up the largest volume fraction of concrete, typically a massive 70% to 80% of the total volume. They're definitely not just inert filler taking up space. They provide the essential bulk, yes, but they are crucial for the concrete's strength, stability, and durability. Specifically, the coarse aggregates are primarily responsible for the concrete's compressive strength. They form a strong skeleton within the paste. And they also play a significant role in preventing excessive shrinkage as the concrete dries and hardens, because they are dimensionally stable compared to the cement paste.
Okay, so the rocks provide the strength and stop it shrinking too much? Does the size of the rocks matter?
Immensely. Size matters a great deal when it comes to aggregates. Coarse aggregates typically have particle sizes around 20 millimeters, about 34 inch, for general construction. But the optimal maximum size depends heavily on the specific structural element being poured and, crucially, the spacing of the steel reinforcement bars inside the formwork. For instance, you might use larger aggregates, say 40 millimeters, in a massive concrete foundation or a thick column where the steel bars are spaced far apart. Larger aggregates can sometimes be more economical and provide good interlocking. However, you absolutely need to use smaller aggregates, maybe 10 millimeters or 20 millimeter maximum, for thin slabs or beams and columns where the reinforcement steel is closely spaced. Why? To ensure the concrete can flow properly and completely fill the space around and between the rebar without leaving any voids or gaps, a problem called honeycombing. If the aggregate pieces are too large, they simply won't fit through the gaps in the steel cage, leading to weak spots in the structure. So the coarse aggregates form the main structural matrix or skeleton of the concrete, providing its primary load-bearing capacity. The fine aggregates, the sand, then serve a vital role by filling the voids and gaps between the coarser particles. They act as a filler in that sense, creating a denser, more cohesive mix, preventing the coarse aggregates from segregating or settling out, and ensuring a uniform solid material throughout.
Okay, so the sand fills the gaps between the bigger rocks, all held together by the cement paste glue. It makes a denser, more solid mass. How do we classify these aggregates, apart from just big rocks and sand?
Right. Beyond just size, coarse versus fine, aggregates can be classified by their geological origin. Natural aggregates are the most common type. These are derived from naturally occurring rock formations, igneous like granite, sedimentary like limestone or sandstone, or metamorphic like quartzite, that are quarried from the earth, then crushed, and finally screened or sieved into specific size fractions. These are your typical gravels and sands, sourced from riverbeds, glacial deposits, or rock quarries. Artificial aggregates, on the other hand, are man-made. These are often produced from recycled materials or industrial byproducts. Examples include crushed and screened broken bricks, especially over burnt bricks, which can have surprisingly good compressive strength despite their irregular shape. Using crushed bricks is an excellent way to repurpose construction demolition waste. Another common artificial aggregate is processed blast furnace slag, that glassy byproduct from iron and steel production. It's often used for its density and good binding properties with cement. Using these artificial aggregates helps conserve natural resources and reduce landfill waste. We also classify them by size, as we discussed. Coarse aggregate. Particles that are retained on, or larger than, a 4.75 millimeter sieve. That's about a number 4 sieve in U.S. terms. Fine aggregate. Particles that pass through that 4.75 millimeter sieve. So sand, essentially. Sometimes you might encounter all in aggregate, which is a pre-blended mix containing both coarse and fine aggregates in suitable proportions, though usually engineers prefer to control the amounts of coarse and fine separately for better mix design. And finally, and this is really important for concrete properties, we classify aggregates by their shape. The shape of the individual aggregate particles significantly influences the concrete's workability, how easily it flows and compacts, and its ultimate strength and durability, mainly by affecting how well the particles pack together and how well they bond with the cement paste. rounded aggregates. These are naturally weathered and smoothed by water action, like pebbles found in riverbeds or on beaches. They offer excellent workability because they slide past each other easily, meaning the concrete flows readily and requires less water and less effort to place and compact. They also result in fewer voids between particles. However, their smooth surface leads to poor mechanical interlocking and weaker bonding with the cement paste, which can potentially reduce the overall strength, especially for high-performance concrete, where bond is critical. Irregular aggregates. These are partially rounded or shaped by attrition, maybe naturally broken gravel. They offer a kind of balance, better bonding than rounded, but perhaps slightly less workable. Angular aggregates. These are produced by crushing quarried rock. They have sharp, angular edges and rough surfaces. They provide the best mechanical interlocking between particles and the strongest bonding with the cement paste, resulting in higher strength concrete. However, their irregular shape creates more voids within the mix compared to rounded aggregates. This means you typically need more cement paste, and potentially more water, to fill those voids and achieve good workability, which can affect cost and shrinkage. Now, there are also undesirable shapes we try to avoid. Flaky aggregates. Imagine a thin, flat pebble that's flaky. Technically, its least lateral dimension, thickness, is less than 0.6 times its mean dimension, average size. These are generally very undesirable because they don't pack well. They tend to align horizontally, creating planes of weakness. They lead to poor bonding with the paste, and they significantly increase the void content, making the concrete weaker and less workable. It's like trying to build a strong wall by stacking dominoes flat instead of using solid bricks. They just don't interlock efficiently. Similarly, elongated aggregates. These are long and slender, with their length greater than 1.8 times their mean dimension. Like flaky aggregates, they are generally avoided. They contribute to poor particle packing, poor bonding, higher void content, and can also break easily during mixing and placement, compromising concrete quality. And the worst combination, of course, is flaky and elongated aggregates, which exhibit both undesirable characteristics and are particularly problematic. Engineers and aggregate producers go to great lengths during aggregate selection, crushing, and screening processes to minimize the amount of flaky and elongated particles, ensuring the aggregates meet strict shape criteria for optimal concrete performance. This quality control is vital for ensuring the final concrete will be strong, durable, and easy to work with. That's why you often see large washing and screening plants.
You know, we walk on it, we live in it, we drive over it. Concrete is just everywhere. It's such a fundamental part of our built world, isn't it? We probably take it for granted most of the time. But how much do we really know about this incredible material? You know, the stuff that literally underpins our modern civilization. Today, we're taking a deep dive into the fascinating world of concrete technology. Get ready to have your perceptions, well, cemented.
Indeed. And it's funny you say cemented because when we talk about something being concrete, we mean